That many at all. Okay, calculus students, are you ready for part two? If you understood part one, then you are gold. You are the golden children because part two just bounces back and forth from the second derivative. And the other lesson, we started with f of x, and we talked about what does it mean when a derivative is equal to zero, the derivative is less than zero, and so forth. But what if we start with the second derivative function? They could give it to you as f double prime is something. Well, if you solve the second derivative set equal to zero, and we're looking for critical numbers, remember those were critical numbers where the values are zero or undefined. In other words, if I had f double prime of x equals to x minus 5 squared times x plus 1, then what we're doing is we're setting the derivative. Let me do one more. Let me go divided by x plus 2. By looking at this, we know that if I set this second derivative equal to 0, then what I'm doing is basically just taking the numerator and saying, well, x could be a 5, and there's two of them because it's a squared, or x could be a negative 1. If I set the denominator equal to 0, that would be where your second derivative is undefined. That would be x equals to a negative 2. Each of these numbers are critical numbers. Okay? That's what he's asking. What is happening at those critical numbers of your second derivative? Well, if you recall, we set the second derivative equal to 0 to look for concavity, the intervals of the concavity, and to look for possible points of inflection. Okay? So if you have your second derivative and you got your values, then f of x, well, what about these at x equals to a, that equals 0 or undefined? We know just by the first step, it's a possible point of inflection. What can that was that was the function. But look at, he's asking me about the first derivative of that function. Well, if you think about it, the second derivative is the derivative of the first derivative. You could treat it back again to, in our imagination, f versus f prime. What did it mean for your critical numbers of your first derivative be equal to 0? What were those? Do you recall? Where your first derivative is equal to 0, each of these a's are a possible relative max or min, extrema. No different if you're doing the derivative of the derivative. If you were to graph the function of the derivative, then these critical numbers of the second derivative would stand for extremas on the first derivative graph. Make that connection. Where your second derivative is equal to 0 or undefined are extremas on the first derivative graph. Okay, what if your a is greater, your x equals to a is greater than 0 at x equals to a? I mean, not your a, but x is equal to some a, and so it's greater than 0. Well, for your function, the second derivative tells me if your second derivative is positive, that would be a concave issue of your function. X equals to a, if it's positive, would be f of x is concave up at x equals to a. Well, what does that mean for your first derivative? which is just like a function. Not sure what happened. My iPad glitched. So the derivative of the derivative, if it's greater than 0, the derivative of the derivative at some a, well, that just means if the first derivative is positive, wouldn't that mean increasing? Well, what would be increasing? The graph of f prime of x is increasing at x equals to a. The first derivative graph would be increasing because the second derivative, which is the derivative of the derivative, is positive. Obviously, whenever your derivative is less than 0, we think about decreasing when we talk about the function that we were doing the derivative of. So that would be less than 0 would mean decreasing. So f prime of x is decreasing at x equals to a. What does it mean for the function itself, the original function? If the second derivative is negative, then it's concave down. And a is here, and so we know that it's concave down. F of x is concave down. Obviously, for both of those, it means when x equals to a, and for both of those. Okay, what if your second derivative changes from positive to negative? Well, for your function, that would be this. Positive to negative. Concave up, concave down. Well, then x equals to a is very, very special. X equals to a would be here. And since concavity changed from positive to negative, then x equals to a is a point of inflection. See, up here, we identified it as a possible point of inflection. But here, we've established that it is a point of inflection. That also applies to if it was concave down and then switched to up, then A would represent a point of inflection. Well, what does that have to do with the first derivative? Now remember, the second derivative is the derivative of the derivative. If your derivative ever goes from positive to negative, that always meant a relative something. Relative what? It went from positive to negative. Oh, well, that meant your graph, this is the graph. We're talking about the graph of the first derivative, would have a relative max. F prime of x has a relative max at x equals to a. And obviously, if you're changing, if the derivative of the derivative was negative, then become positive, that became f prime. The graph of f prime of x has a relative min. This is the key of today's lesson. Just realizing that you should be able to look at a graph of either of those and talk about what it means to be the other two functions. Let's practice. Consider this derivative. This is a derivative function, 2x minus x sine of x. Now, he said consider the function based on the graph. We're only going from -5 to 5. Well, I don't have a graph in front of me. So I'm going to have to get out my calculator, and I'm going to put that graph on here. I'll be back. Go ahead. You get a head start. Abracadabra, there it is. So let's take a look at the graph of h prime. I think I will go to a blank page and just put it there again, nice and large. Let me just save this, hold on. Okay, let's take a look at it. And basically I could still just zoom in here too and look at it, see the same thing. Based on the graph of H prime, how many relative extremas are there? Well, as I said, there's one. Because that's where, and he wants to justify us. H prime of x equals to 0 are where that's your critical numbers, your x values. So that's where your relative extremas will be. Since I only have one H prime equals to 0, then I can say there's one extrema. I can even be more detailed and say that to the left of that extrema, the derivative is always negative. And to the right of that extrema, it's always positive. So therefore, it looked like this. Negative, positive. It's actually a relative min, in case they asked. But while we're on it, the second picture says, based on the graph of the derivative, how many points of inflection does the graph of h, the original graph, would have? Well, interesting about that is points of inflection is wherever concavity changes. So concavity would change when the second derivative is 0. Since this is a graph of the first derivative, I have, let me do a different color. I have a 0 here, a possible 0 here, possible 0 here, possible, I can't tell, and I could be wrong. I know I have one here, and I know I have one here. I can't really decide if I have one to the right of 0, 0, before I get to over here. So maybe I'll look at the other picture that I have, if you recall back, and say, based on the graph H prime, how many points of inflection, which I would say there was 4, and we have to say because the, let me do that, the derivative, which is h double prime of x, of the derivative, the derivative, which was h prime of x, which is the picture of the graph, has relative max or mins. Basically what we're saying is this, where h double prime of x is equal to 0, where the slope is 0, horizontal tangent. Find the equation of h double prime. They want us to do it by hand. Then we'll graph it and we'll compare our responses. So let me remember what h prime was. H prime of x was equal to 2x. I think I can go back up and look. Minus x sine of 2x. Minus x sine of 2x. This is going to require product rule with this component and chain rule with this component. So here comes the fun. Isn't that the Beatles saying? Here comes the fun. La 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 la. H double prime of x is a 2 minus something. I'm going to take this and do my product rule. The first times the derivative of sine of 2x, which has the chain rule. So I'm going to just write it times 2 cosine of 2x. plus the second sine of 2x times the derivative of x, which is 1. There it is. And so I could clean that up with my calculator. I'll go 2 minus 2x cosine of 2x minus sine of 2x. That's what I'm going to key in my calculator. We're going to look at that graph, and we're going to see if what I am suspecting is true based on the graph of h prime. And if I'm right, it means I did a lot of analysis of the second derivative by just looking at the first derivative. So you should pause at this time, do it yourself. Okay, I went and graphed the second derivative. And what did it look like? I'll post it in a second here, but there was, what did we write? I wrote it here. It's really 5. There was, I got it counted here. 1, 2, 3, 4. I had it there, I just didn't count it. Maybe one of you saw that. I don't know. Anyway, let me go and get that picture of that derivative, and I'll be right back. And there it is. And if you look carefully, just as I was saying, that there's a second derivative that is equal to 0. That means the derivative of the derivative. So the original derivative must have a max or min there. There's that one. There's that one. There's those 3. Then there's this one and this one. Now, what I'm going to do is I'm going to show you both pictures together so you can see the relationship between the second derivative and the first derivative. The behavior is just like looking at the derivative versus the original function. It's the same thing. Whether you go function derivative or first derivative, second derivative, the behaviors that we describe are the same. Okay, see the second graph? The pink is the original h prime, and the green is h double prime. And so the green stands for the same. If you remember the marks that I made, this correspond to a max or min. Think of it as pink is the original function, even though pink was the first derivative. And green is the derivative of the first derivative. So this is my h double prime, and this is my h prime. Notice, keep going here. There's a 0 of the second derivative, corresponds to a horizontal tangent location. Then we have a third one here. 0 of the second derivative corresponds to a horizontal tangent where the slope is 0. Moving to the right, I have the green one with a 0 here, corresponds to a horizontal tangent here. And was there another one? Right here, 0, second derivative, stands for that the first derivative had a horizontal tangent. I hope you see the connections that are being made. Let's move on. There it is, from -5 to 5. And so we're going to have to realize that he's going to be asking us for where are there max or mins on the original function. Since that's the first derivative, max or mins would occur when the derivative is 0. And since I just graphed the derivative of h right here, so let's go back and see what was being asked. That picture, and see if there's any possibility. As I trace through here, I don't see any possibility that the derivative is 0. But I do have a 0 derivative. The derivative of this graph, which was the h double prime. I have those two for sure. As I travel this way, I think I'm getting a 0 here, and I think I'm getting one here. So it looks to me like if I had to be a betting man, I would say 4 possible points of inflection. Because remember, a point of inflection occurs when h double prime of x is equal to 0. That means the derivative of the derivative. And this pink one is the derivative. So with the derivative of the derivative, when the slope of the derivative graph is 0, which would be tangent lines being horizontal, I think I can rest my case on that one. It looks like I only counted the 4, and I wasn't convinced that there was another 0 here, but somewhere in here, I think the graph shows me there's another one. So, or was it there? Oh, wait a minute. It wasn't there. Who am I trying to kid? Maybe you already saw it. Let me get rid of this. It wasn't there. I already had 2 over there. Why didn't I pick this one? There's that one. There's 5. Okay. So we got to go back and change that into our lesson. And oh, there's that beautiful picture. So let's wrap this up here. Based on the relationship between a function and its first and second derivatives, if f of x is increasing, that means f prime, the derivative of that function, must be greater than 0. If the function is decreasing, then, and it goes both ways. See the both way arrows? You can go both ways. Then the derivative must have been less than 0 underneath the x-axis. If f of x has a relative max or min, what can I say about the first derivative? Equal to 0. If f of x has a point of inflection, what does that say about the first derivative? F prime, I'm trying to think what happens. Let's see, point of inflection. You have from concave down, then, okay, right here. You see what happened here? You have, that's a point of inflection. I don't see what's happening to the derivative. The derivative looks the same slope, just on different sides of the f of x has a point of inflection. F prime of x, I got to leave it blank for now. If f of x is concave up, then the second derivative must be greater than 0. If f of x is concave down, that's this was concave up, then the second derivative is less than 0. If f of x has a point of inflection, then the f double prime is equal to 0. That, not bad. If f prime is increasing, so that's the increasing that we pretend it's just f of x. Just pretend if f was increasing, what would the derivative be? Greater than 0. So if f prime is increasing, then f double prime is greater than 0. If f double prime is decreasing, it's acting just like a function related to the first derivative, but this is first derivative related to the second derivative, less than 0. If f prime has a relative max or min, what does that mean about the second derivative? Well, the second derivative is equal to 0. We just showed that in that big graphs we had. Another one, if f prime has a point of inflection, if the derivative has a point of inflection, then this is going to talk about what does it mean about the second derivative if the first derivative has a point of inflection? I'm going to have to say it's the same situation I have here. If f versus f prime, f prime, I have a feeling what they're thinking about is that if there is a point of inflection on the graph, that meant something had to go up versus come down. You had concavity there. That if f has a point of inflection, then they're probably f prime of x. F prime of x. F prime of x would have to have a relative max or min. Oh yeah, it makes sense. If that'd be like the second derivative, same thing happening here, then f double prime would have a relative max or min. That's my guess if I had to bet money. What if your first derivative changes from negative to positive? That's the same thing as saying, what if your function changes from negative to positive? Wouldn't that be saying that I possess a max or min? Yes, it would. Except from negative to positive means it has a relative min. If it changed from positive to negative, then f of x has a relative max. If your first derivative has a relative max or min, if your first derivative has a relative max or min, then f of x at that place must have a point of inflection. If your second derivative changes from positive to negative, then f prime of x has a relative positive to negative max. If the second derivative, which is one up from the first derivative, goes from negative to positive, then it has a relative min. All right. For the rest of this lecture, you're on your own. For your lecture packet grade, work with your partners, and here's a chart. We're going to be looking at 15 cards. We could have just as well mixed them up, and they're on the following page. Oh, where am I moving? Chart. And decide which three would you group together. Is 7 the function, and I'm not writing anything. 7 could be a function, 11 was its derivative, and 12 was the derivative of the derivative, meaning second. This is just, I'm saying, that could be f, that could be f prime, that could be f double prime. You got to talk about it, look at the characteristics, and discuss and see. And let's see. The first group that can send me a picture and remind of a complete table wins a special treat when I see you next. Once you get done, there's 1, 2, 3, 4, 5, 6, 7, 8. Go back to with that activity, 9, 10, 11, 12, 13, 14, 15. They're all labeled a number, okay, 1 through 15. You need, your homework is homework 37. Okay, I'm going to call it quits. Bye-bye.